All right, welcome back. So we are still in Unit B. We're on Chapter 2 of Acid Deposition. And this is Lesson 1.2. And we're going to start looking more closely at the chemistry of acids and bases. So by the end of this lesson, there are actually a lot of things that you've done in Science 10 and maybe even grade 9. I've started to look at my daughter's work and a lot of it's similar. So hopefully not all of this is brand new to you. So we're going to define acids and bases as either proton donors and proton acceptors. We're going to look and differentiate between acids, bases, neutral ionic compounds, molecular compounds, strong and weak acids, and then look at some diagnostic tests that you can use. We're going to describe the relationship between pH and hydronium ion. This is actually in part 2, so not in today's lesson. Same with indicators. So these will be in part 2 or part B, the next lesson. So there's our textbook pages. Take a look at those if you would like to review on your own. And this is where the video will be posted. All right, so what are acids? Where are acids and bases found? Well, they're found all over the place. A lot of them in our different foods that we eat. There's an example of some different acids and bases that are found at the different pH levels, and how they can actually start breaking down the enamel in your teeth. Some of these acids are quite strong, especially some of these acids that you're finding in some of your pop drinks that you're drinking, especially Coke. This one I just thought was so interesting. Soda pop contains carbon dioxide, phosphoric, and citric acid. As you remember, carbon dioxide actually reacts with water to form carbonic acid. So all three of those different acids could be in your soda pop that you're drinking. And there's an example here of this chicken, like a chicken breast that had been put in Sprite versus Coke. So you can see Sprite versus Coke for 5 days. And you can just see how much the flesh has deteriorated on that chicken that was in the Coke. So that acid was just eating away and deteriorating it. And it does the same thing to your teeth too. So you also find, like I said, in lots of different foods, acids and bases can be found. Baking soda is a base. Alka-Seltzer, Rolaids, Tums. You take these when your stomach is upset. It's because your stomach is full of acid, right? We all know stomach acid is in there. And some people, if they have a very good sphincter here, the reflux can allow some of this acid to start coming up your esophagus and it burns. So that's when you take Tums or Rolaids, or if you're hardcore like my stepdad, he'll take baking soda, he'll put it in a glass of water and stir it and just down the straight stuff. So it's basically all these Tums, Rolaids, Alka-Seltzers, they're all bases. And so is this baking soda. Okay. So why are you taking that? To neutralize the acid. So where else are acids and bases found? Used for all these different processes. So they're very popular. They're very common. They're commonly produced, acids and bases. And out of the 10 top chemicals produced, 3 of them are acids and bases. So they're really important, and it's good. That's why we're studying them, to see how they react with other chemicals. So when acids are in water, they dissolve and they form aqueous solutions. And so to actually have an acid, all acids are going to be dissolved in water. So whenever you see an acid written like this, which that too should be little, this you'll always see the AQ sign, which stands for aqueous solution. You'll always see that right underneath as a subscript beside every acid. Okay. So, acids, they're also considered molecular compounds, kind of. They look like they're molecular compounds, so their formulas kind of show that they're molecular because they're only made up of like non-metals that share their electrons. But unlike molecular compounds that you learned about in grade 10, these will actually dissolve in water, acids. So they behave a lot like ionic compounds. So they break into their ions when they go into water. And so their solutions are able to conduct electricity, just like ionic compounds. So acids will conduct electricity just like ionic compounds. Molecular compounds do not conduct electricity. All right, so how else can we identify acids and bases? So we talked about the conductivity. So strong acids and bases are more conductive than weak ones, but they will conduct in water. So they can actually transfer a current. You probably use litmus paper in grade 10 or grade 9 at some point. If you put if you test a base with litmus, it'll either turn blue or stay blue, whatever litmus paper, doesn't matter. And if you're testing an acid, it'll turn red in litmus. So you may have learned that BB, bases turn litmus blue, and then acids turn it red. We can also taste them, although this is not very safe way, and I don't recommend anybody taste if it's something as an acid or base. But acids taste sour, so you've probably tasted some acids before. Citric acid, very common acid on those sour candies that we all love. Yeah, citric acid, that's what that is. It tastes very sour, whereas bases taste really bitter. So if you go and have some of that baking soda and just taste it, very bitter. You don't like that. When you eat a muffin and the baking soda hasn't been like all dissolved nicely in the, and you get like a little ball of it and taste it, it's horrible. Anyway, the other way to test for acids and bases, probably the most accurate way, is using a pH meter. So you can actually stick the pH meter in, it's got electrodes in it, and it'll tell you the pH. So we're talking pH again now. So what is the pH scale? Well, it's a scale of 0 to 14, where from 7 to 14, we're looking at bases. At 7, we're looking at neutral ionic and molecular compounds. And between 0 and 7, we're going to be talking about acids. And there's some examples of how different acids might lie on that pH scale. So there's been work over time on defining acids and bases, and we're going to look at two different definitions. The first one is Arrhenius. So to understand Arrhenius's definition, we first have to look at dissociation and ionization. So, and this dissociation is the separation of a chemical substance into its individual ions. So like ionic compounds, when you put them in water, they split into their two ions. So this is true for bases. These dissociate. So there's an example here of sodium hydroxide. Dissociating into the two ions that form sodium hydroxide. You have the sodium ion, which is sodium positive ion, and then you have the hydroxide ions. And these hydroxide ions are what Arrhenius defined bases as. Bases are compounds that dissociate to form hydroxide ions. Okay, whereas acids are compounds that dissociate to form hydrogen ions, these H positive. Okay, so that was Arrhenius's definition for acids and bases. All right, so Arrhenius also said that neutral compounds that do not dissociate to form hydrogen ions or hydroxide ions, they're neither acid or base. We'll call them neutral. So we don't have an example. Their example, calcium chloride, when it dissociates, they break into their positive ion and the negative ion, and neither of which are hydrogen or hydroxide. So then it's neutral. So if we look at these compounds down along the side here as a little bit of practice, here we have hydrogen ion attached to the nitrate ion. All right, so that's why it's considered an acid. And a lot of times the acids that you're seeing with Arrhenius's definition, they all start with hydrogen, the majority of them. Something like sodium sulfate, if you break it into the ions, you've got your metal ion of sodium positive, and you have your sulfate 2 negative ion. So there is no hydrogen ion and there's no hydroxide ion. So that is why that is neutral. Now, you have a hint with this next compound. It starts with a hydrogen. It's going to be an acid. It's going to break into the hydrogen ion and then this nitrate ion. Here's an example of a base. So we have barium. So there's your metal ion, and it's going to break into the hydroxide ions. So acids usually begin with hydrogen and bases usually end with hydroxide, as you've just seen. However, this is not always true. There are lots of acids that end in something like this, which I think of as Cu. And in this case, that hydrogen there would be the one that would be dissociating. You also have bases, something like ammonia, that do not have hydroxide. There's no hydroxide in them, but yet they're still bases. And this is where Arrhenius's definition kind of fails. And so we get another definition coming into the picture. Before we talk about that next definition, let's just see what hydrogen ions actually do when they're in water. So when they're in water, they don't stay as hydrogen ions. They actually react with a water molecule. So you can see there's your proton or your hydrogen ion reacting with the water molecule to form hydronium. Hydronium, there's how it's spelled. And these hydronium ions are positive still. And high concentrations of solutions with hydronium ions are what make up acids. Okay. Still, if you have a high concentration of hydroxide, that is considered a base. So we have a new definition here, and this is using Bronsted-Lowry theory. And this is where we're using the idea of who's donating the proton, who's accepting the proton, and that there's hydronium ions are present when we have an acid. So for Bronsted-Lowry, we need to figure out who is donating a proton in a reaction, and that is going to be called our acid. Whoever's accepting the proton is the base. And remember, a proton is just a hydrogen ion like this. Okay, so keep that in mind. You've got a proton donor, so somebody throwing the hydrogen to somebody else who's catching the hydrogen, which is going to be considered our base. So here's kind of like a simple diagram version of this. We've got hydrochloric acid, HCl, and we've got water. And the hydrogen chloride, or the hydrogen here from this acid, it's represented by this blue circle, is being donated to the water, and the water is accepting it. So the water now, as a product, has 3 of these blue circles, which are representing the hydrogens. 1, 2, and then it gained one over here. So the water is the hydrogen acceptor, and the acid here, hydrochloric acid, is the hydrogen donor. This leaves the hydrochloric acid with this chloride, and the water becomes hydronium. Here's another drawing out the exact same equation. We talked about hydrochloric acid. It's our proton donor. The water is acting as the proton acceptor. Now, when the water turns into the hydronium, it was the base, and now we call that hydronium the conjugate acid of the base. Okay, so it's our conjugate acid. For the acid, the hydrochloric acid, when it donates the hydrogen, it's left with just the chloride ion. And this is called our conjugate base of the acid. Okay, so we have acid, conjugate base, base, conjugate acid. The only difference between each of them, if you'll take a close look here, the only difference between this conjugate base and the acid, when you look at it carefully, the only difference is the hydrogen atom. The proton is gone. The only difference between our base here and our conjugate acid is that a proton has been added. Okay. Well, we'll take a little bit more here. This is actually a video. I know you can't see the line around it, but it's a great video about conjugate acids and base pairs. So if you're still kind of a little confused after this, definitely go and take a look at that. And then this video explains the Brownstein-Lowry theory and how hydronium ions are formed. Also, some great examples of acid-base reactions. So in your data booklet, this is a chart that you're going to use quite a bit on page 12 of your data booklet. This is going to help you figure out the relative strengths of acids and bases, and to identify conjugate acid-base conjugate pairs. So all our strong acids are up at the top left of the chart. Hydronium, and these three acids above are all considered strong. Okay, they're all considered the strongest acids. That means when they go into water, they 100% all form hydrogen ions, like all of it. Then we have all these acids below the gray line, and they're all considered weak acids. So they still form acidic solutions, just nowhere near as strong as the ones above. And then for bases, okay, so first, let me just say, so these are your strong acids. There we are. There's your strong acid formulas. These are the names along the side. And then these are your weak acids. Weak acids. And you might even want to be writing this on your chart. Right? And these are your strong ones. Now, when we're talking bases, it's the other way around. The strongest base is at the bottom, and there's only one strong base, and that's the hydroxide ion. So if you have a compound that contains the hydroxide ionic compound, then that base will be a strong base. All the rest of these bases here, actually all of them will be weak bases. And you'll see that water, let's get that into a nice blue green color. Water appears on both sides. Water can act as a base or as an acid. And there's a few things that can do that. They can either accept protons or donate them. So, just a little aside here on strength versus concentration of acids. They're not the same. When we say an acid is strong, that does not necessarily mean it's highly concentrated. So concentration is the amount of substance in a solution in moles per liter. So how much acid per liter there is. The strength of an acid depends on how well it dissociates, right? Remember, it has to dissociate and donate a proton. If it's really good at donating protons, then it's very strong. Okay, so you can have two acids with the same concentration, but they are different strengths. So something like you could have vinegar, which you can put on your fries, and you can have hydrochloric acid at the same concentration. But the hydrochloric acid is a much stronger acid, so it's going to donate a lot more protons easier, and so you'll have a much lower pH. So strong acids dissociate completely in solution, so their hydronium ions are high, and therefore their pH is lower. Weak acids only partially dissociate, so they don't give all of those hydrogens protons away. They don't donate all of them. So that leaves the hydronium ions lower, and the pH is a little bit higher than these strong acids. And we're going to be exploring pH and hydronium ions in much more detail in the next lesson, or the part B of this lesson. So before we head off, we're going to take a look at conjugate acid, conjugate base pairs, remembering that acids lose a proton to become more negatively charged, and bases accept protons. So our acid basically has to always have one more proton than the base. So Another way you can look at this, take a look at that chart on the page 14 as I do this, and you'll probably find all of these acids and bases on that chart, and they're beside each other, these acid conjugate base pairs. So when this acid goes and reacts with a base, it's going to donate a proton, right? It's going to donate a proton, and what is it going to look like? So it's losing a proton with the positive charge, but it's leaving the negative charge behind. So there's going to be one hydrogen left because it had two. SO4 is still there because it's going, SO4, it's going nowhere. It's only the hydrogens that change. So SO4 is here. It's still aqueous, but now it's going to have a negative charge because the proton didn't take the negative charge with it. So let's go the other way around. So if this is the base and the bases act as a proton acceptor, so we're going to add a proton to this base, this water. You're going to add an extra hydrogen. So now instead of 2 hydrogens, it has 3 hydrogens. It also has an oxygen, it's a liquid, and it's going to have a positive charge because the proton brings a positive charge with it. Let's try one more here, and then you can try some of the other ones on your with your data booklet. So in this case, this acid here, it's gonna donate that proton, bye H, and it becomes one more negative. So we are just gonna have no hydrogens anymore. SO4, and it was 1 negative, and now it's 2 negative. Let's try a couple more here. Acid, we're going to lose one of those hydrogens, right? Proton's going to pop off. And when you're dealing with these ones that say COOH, C-O-O-H, these acids, that last H is the one that is donated. So we're going to lose that last proton and become negative. There's your acid with the aqueous symbol too. Now let's take this base. Let's go backwards with it. We're going to give it a proton, so it's now got 2 hydrogens. And we're giving it a positive charge, which is going to cancel out the negative charge that it has. So now it has no charge. Right? It had negative, but we added a proton that has a positive charge as well. So hopefully you start to see the pattern here. I'll do these last two forward if you don't want to watch them. This is an acid, it's gonna donate and get rid of a proton, and it's going to become NH3. It's only got 3 hydrogens now, and it's losing a positive charge, so it's just NH3. Now, if you haven't noticed this, make sure you look on page 14 of your data booklet, and you'll see all of these are on there, and they're right beside each other. You can go back and forth and see them. Last one, hydroxide ions. It gains a proton, so it's going to get an extra hydrogen, so it's now 2, and a positive charge, which cancels out the negative charge, so OH2. Well, what's that? H2O, just reorganized. There you go. All right, so this is how you figure out the acid and the conjugate base pair. Remember, this is what the acid turns into once it reacts with the base. All right, so there's an example problem here from your textbook. We're going to take a quick peek at. This, again, is in your textbook. I didn't write the page number down, but you can see it's a sample problem, and it's written out in all the steps in your textbook. All right, with this sample problem, you're going to be writing an acid-base reaction. All right, so the question says we have sour gas which contains hydrogen sulfide, and it can dissolve in water. So write the chemical equation of the reaction between aqueous hydrogen sulfide and water. So we have 2 substances, and we need to figure out what's our acid, what's our base, and what's this reaction going to look like. The first thing we do is we try and find these 2 substances in our acid-base chart. So first we look in the acid chart and we see what we have. Well, water shows up always on both sides, and then you'll see H2S is showing up here. So it's also an acid. Water can also show up on the base side, but if you look really carefully, you are not going to find H2S there on the base side. So, and which one's the strongest acid? Well, strong acids are always near the top, so our strong acid is going to be the one that reacts. So H2S is going to be our acid. H2S, aqueous. This is our acid. Then we're going to react it with our water, which is our base, H2O. Now, how do we figure out what our products are going to look like? Well, our chart gives us a real sneaky way of doing this. We can see H2S, it gives us what the conjugate base looks like. So when H2S donates its proton to water, it's going to lose a hydrogen. It only has one hydrogen now. Still has a sulfur, but it becomes negative. And look, they give it to us in the charts. We don't even have to memorize it. We don't even have to figure it out. We can just look in the chart to see what that acid turns into when it reacts with the base. All right, and then what about the water? What's it doing? Well, it's the base. It's acting as the base because it's accepting the proton. And so it's now going to have 3 hydrogens. And it's going to have an extra positive charge as well. And if we look at the water in our base chart here, and we look to its side beside it, you'll see that is exactly what we have. So the base turns into its conjugate acid. And our acid turns into the conjugate base. And that is our acid-base reaction that's occurring. I strongly recommend you do a few more of these practice questions. And we're going to pause right here. That's the end of part A.